In my talk, I want to present you a method how to quantify the effect of manufacturing defects on the fatigue life of additively manufactured materials. That's the example of titanium aluminides. Let's come to the motivation. Titanium aluminides are an intermetallic alloy of titanium and aluminum whose properties are between those of ceramics and metals. One application for titanium aluminides are the low pressure turbine or the blades of the low pressure turbine of modern aircrafts, like here the Airbus A320 Neo. They are very suitable for this application since they meet the high requirements regarding strength, stiffness, density, and high temperature resistance. But there are also some challenges like the brittle failure and damage tolerance, which makes this material very sensitive for local defects, which affect the mechanical properties. Due to the low ductility, the linear elastic fracture mechanics is valid for the most applications of this material. Here in our study, we investigated the third generation titanium aluminide alloy TNM. This alloy was processed by the additive manufacturing process of electron beam powder bed fusion with ACAM A2X. We can see here the process parameters. All specimens were manufactured orthogonally to the building direction, then separated with wire cut EDM, turned in the here shown specimen geometry, and then the surface was polished to exclude the influence of the surface in the first step. We investigated two conditions. First, the as-built condition with no further heat treatment or hot isostatic pressing, and the additionally hot isostatic pressed condition. We see here shown parameters for the hot isostatic pressing. First of all, in both conditions the same microstructure occurred. So this was this lamellar alpha-2 gamma structure, the light beta O phase, and the globular gamma grains, which can we see here a little bit better. But due to the high temperature at the hot isostatic pressing process and the low cooling rates, there was a significant grain coarsening. We performed constant amplitude fatigue tests, which were stress controlled with 20 Hz frequency, a stress ratio of -1. The tests were performed at room temperature and at the application temperature of 800 degrees Celsius using a high temperature furnace. After every test, we observed the fracture surface with an SEM to find the location and the size of every fracture-inducing defect, also called the killer defect. And this was possible for every specimen that we tested. Let's come to the first result. We see here the SN curve, so the stress amplitude versus the number of cycles to failure. In blue, the as-built state, and in red, the hot isostatic pressed condition. The darker color represents the tests at room temperature, where the lighter color represents the tests at high temperature. First of all, we can't find a significant difference between both testing temperature, indicating a very excellent high temperature fatigue strength for this application. But we saw a significant improvement of the fatigue strength by the hot isostatic pressing. But on top of this, there was a very high scattering, which we can see at these error bands here. Okay, the question is, what's the reason for these two levels and the high scattering? To understand this, we did this spectrography and found overall 3 different types of failure. First of all, lack of fusion defects. Then microstructure features, mainly lamellars, which detected like a crack. And when they had an orientation orthogonal to the direction of the highest force, there the failure occurred. And last, gas porosity. Now in our SN curve, we have marked these different types of failure. And we can see that for the as-built condition, mainly lack of fusion defects lead to failure, and in some cases gas porosity, where for the hot isostatic press condition, gas porosity or this microstructure feature lead to the failure. And further, yes, so we can conclude that due to the hot isostatic pressing, these lack of fusion defects have been closed in such way that they did not reopen again during the test, and healed that they even not reopen again under the high temperatures. Yeah, and maybe also the size of the defect was reduced, but to yes, prove this, we have to first of all measure the size, and we did this by the square root by the square area approach. So we measured the square root of the projected critical defects. So in this example, the red area. Now in the SN curve, I have marked the color-coded the defect size, and we can see that we can see that the defect size was significantly lowered by the hot isostatic pressing. At the as-built set, we had defect sizes up to 200 micrometers, where for the hot isostatic press condition, it was, let's say, around about 100 micrometers. The problem is that everything I explained now cannot be shown with help of the SN curves, because the SN curve is only can only be used for homogeneous materials, and additive manufacturing materials are not homogeneous. They have always these local effects at the defects. And yeah, so we need another approach, and yeah, I will show you the method now. First of all, we use the Murakami approach. So Murakami describes this approach describes the local stress intensity factor at a special defect, taking into account the stress range from the test, the location of the defect. So if it's located at the surface or if it's an internal defect, and the already known defect size. So yeah, now starting from our SN curve with two levels, very high scattering, we go now to another representation. We go to the so-called Shiotsuba curve, which plots this cyclic stress intensity factor versus the defect-related number of cycles to failure. So the number of cycles to failure normalized by the defect size. And we can see here that the entire defect-depending fatigue life can now be described with one single straight line with lower scattering than before. And this is valid for all types of defects, for both microstructure conditions or the temperatures, and even for the full range of the defect size. Yeah, the good thing is that we can describe this behavior here with help of an equation, this Shiotsuba equation, which takes into account the Paris-Erdogan law. And for our special condition, we can now calculate these constants C and M for from this equation. And if we take these now known constants, first of all, take the Murakami equation, the Shiotsuba equation, set them equal to each other, and transform them to a new equation, we can find here a formula for the stress range based on the defect size, the location, and the number of cycles to failure. And in the next step, we use this equation to calculate synthetic SN curves, or in other words, defect-based local SN curves for a special defect size and a special defect location. And with help of these SN curves, we can now describe the effect of defects. And here to prove them, we plotted the data points from the real experiment you have seen before, and we can see that for volume defects and even for surface defects, it fits very well. And in the next step, I show you how we want to implement this knowledge now in a process monitoring to make a decision directly during the manufacturing about the fatigue performance. Therefore, we used the method of the electron optical imaging. I will not explain this method in detail, but it's in short, it works like the following. During the electron beam powder bed fusion process, we use an electron to melt the surface in every layer. And during this melting, you know from an SEM that there are different signals. And these signals are measured with a sensor. And taking these BSE signal, we can then make optical images of the surface. And yes, beside of these optical images, we can find defects directly during the manufacturing. So how does the method work? We start with the electron beam powder bed fusion process. And then first of all, for a new material, for a new set of parameters, we have a one-time experimental determination of the effect of defects. So exactly the method I showed you before. So starting with the SN curve, the Shiosawa curve, and then finding the equation for these artificial or local SN curves. Then when we are manufacturing our real part, layer by layer, we make a scan for every layer to find the defects and their characteristics, so the location and the size. And then taking both information together, so the characteristics and the knowledge about the effect of defects for this material, we can calculate the local stresses in every layer. And then doing the manufacturing, we can make a decision. So if the specifications are not matched, we can reject the part directly there and save time. Or the specifications are met, we have a good part, can continue the manufacturing, or if not sure in detail, we should make a post-examination, for example, with a CT. So the overall goal for this method is a real-time evaluation of the defect-depending fatigue life during the additive manufacturing process. Here you see some publication on these topics with more details. And finally, I want to acknowledge the German Research Foundation for funding the two projects where these results come from, and my project partners from Dresden and Erlangen-Nürnberg for the excellent scientific collaboration, and you for your attention.